Good evening again to the live session for the course Advanced Concrete Technology. So, today we will discuss the topics which were covered in the week 6. Without further ado, let's move to the questions. Let me share the screen. Yeah. Is my screen visible? Yeah. So, thank you. So, without any further delay, let's move to the session. So, in the week 6, we dealt with mineral admixtures and we introduced several mineral admixtures such as basics of mineral admixtures and then about fly ash, slag, rice husk ash, etc. In the coming week, we'll learn in detail about each of them. So let's move to the first question. Supplementary cementitious materials are chemical admixtures, mineral admixtures, they are added to densify ITZ, or they are waterproofing chemicals. So, supplementary cementitious materials, they are chemical admixtures, they are mineral admixtures, they are added to densify ETZ and waterproofing chemicals. Okay, so the correct answer is that they are mineral admixtures and they can densify ITZ because they attack onto or they make the portlandite react with the amorphous silica and produce calcium silicate hydride, which reduces the porosity and also which reduces the calcium hydroxide content in the ITZ. Yeah. Moving on to the next question. The hydration product which is easily attacked. One second. Yeah. So the hydration product in normal concrete systems which is easily attacked or chemically attacked. In order to refine the question, let's say which can be easily chemically attacked. Is it CSH, CH or Portlandite or AFT that is ettringite, or is it AFM that is monosulfate? So Shrish, KPC Rao and Naveed has commented. Okay, so I got different answers like CSH, CH, and AFT. So which is more vulnerable to chemical attack is the question. So which is the hydration product which is more vulnerable to chemical attack? Okay, so let's move to the question. Sorry, answer that is CH, that is Portlandite. So in that in any case, even when the mineral admixtures are added, they utilize the Portlandite and produce the additional CSH, as a result of which the carbonation resistance, etc., decreases. That's because Portlandite stays as a barrier. So whenever some deleterious element comes into the microstructure, it reacts initially with the Portlandite, or when the carbon dioxide gets into the system, it initially reacts with the Portlandite or calcium hydroxide. So calcium hydroxide get depleted. Only after that, the CSH will get affected. So the hydration product which can get easily attacked is Portlandite, that is CH, not CSH. Okay, moving into the next one. CSH has a higher surface area than calcium hydroxide. State true or false. So calcium silicate hydrate, it has a higher surface area than calcium hydroxide. State true or false. So this is a comparison between the surface area of calcium silicate hydrate and calcium hydroxide. Whether the calcium silicate hydrate has a higher surface area than calcium hydroxide or not. Okay, I'm getting multiple responses. Good. Okay. So let's move to the answer. The correct answer is true. You know that calcium silicate hydrate has a layered structure with so many layers of material, and in between the water molecules are also present. So that is a Feldman-Sereda model. So that results in a very high surface area. That layered structure results in a very high surface area for calcium silicate hydrate, and it occupies more space than calcium hydroxide. So that is one reason why we add mineral admixtures. That is, the calcium hydroxide will be utilized by these mineral admixtures, so that the amorphous silica or the reactive silica in mineral admixtures can react with the calcium hydroxide and form calcium silicate hydrate having a very high surface area, so that more pore space can be filled. Okay, so the correct answer is true. So moving on to the next question. Arrange the following in the increasing order of calcium oxide content. So this question, yeah, you need to think a little bit. So let's give more time to this one. So arrange the following in the increasing order of calcium oxide content. Option A is states that the class F fly ash has more, and PC, that is Portland cement, has the least. Option B, Portland cement has the least, then class C fly ash, then class F fly ash. Option C, it says class F fly ash has the least, class C fly ash, then comes PC or Portland cement. Option D states class C fly ash has the least of CaO content, then class F fly ash, then PC. So, which might be the correct answer? So, the question is, we have to arrange in the increasing order of CaO content. Mind you, the increasing order of CaO content, calcium oxide content. Okay. So, let's move to the answer. The correct answer is C. So, thank you guys for responding, and all the three responses were correct. So, the correct answer is class F fly ash having the least amount of CaO content in that given options, then class C fly ash, then Portland cement. So if you see the diagram, ternary diagram, then you can be sure that PC, it's more close to CaO, which means that PC has more CaO. Then comes type C fly ash or class C fly ash. Then the least is class F fly ash. So the correct answer is C. Moving on to the next one. Clays are richer in calcium oxide than alumina and are hence cementitious as well as pozzolanic. State true or false. So just remember where are clays in that diagram. Maybe that will help you to answer the question. It says that the clays are richer in calcium oxide than alumina. So it says that more than alumina, there is calcium oxide in clay, and because of that, it is pozzolanic and cementitious. So state true or false. Okay. I got two responses. Okay, three responses. Okay. Okay, let's move to the answer. So the correct answer is false. Why? Because clays are basically aluminosilicates. So more than calcium oxide, they contain alumina and silica. So the given statement which states that it has more calcium oxide than alumina is a wrong statement. Okay. So moving on to the next one. Okay, this is directly from the slides. The calcium to silica ratio in the CSH gel formed in pure OPC is close to 1, 1.5, 1.7, 2. I hope the question is clear. So when pure OPC hydrate CSH gel is formed, so it has calcium, silica, hydrogen. So what is the ratio of calcium to silica in CSH gel formed in pure OPC? Okay. So the options are 1, 1.5, 1.7, and 2. So I have received three responses. All the responses says C, that is 1.7. So yeah, the correct answer is 1.7. So can someone says what happens to the Ca to Si ratio when mineral admixtures are added to it? So this is in the case of pure OPC. What if it is a blended system with mineral admixtures? What happened to the calcium to silica ratio of the CSH gel? So that's not in the presentation, as in that's not given here. I'm just asking, can someone guess or say what happens to the calcium to silica ratio of the CSH gel in a blended system, not in OPC? Will the calcium to silica ratio change, or will it increase, or will it decrease? Come on, get. I think it was conveyed by Sir, discussed by Professor Manu.
It decreased my
Calcium to silica ratio decrease. Why?
ma'am as ma'am because these cementitious material these admixtures
Mineral
are
admixture. Huh.
mineral admixtures are siliceous in nature, more siliceous in nature. That's why they tends to decrease this ratio.
Yeah. That was Naveed. Was it Naveed? No. Shrish. Was it Shrish? I couldn't see that time.
Yes, ma'am.
Yeah, okay. Thank you, Shrish. So, what he told was perfect. So in mineral admixtures, we need reactive silica. That's why we are choosing mineral admixtures based on the reactive silica content. And when this reactive silica is more in the system, the calcium to silica ratio, that is silica comes in the denominator. So as much as the silica content is increasing, the calcium to silica ratio tend to decrease. So that happens in the case of any system with the mineral admixture. So it will be lesser than 1.7 or 1.8 for sure. So let's move to the next question. This is also related to calcium to silica ratio. So what is the calcium to silica ratio in the latent hydraulic materials? So one example for latent hydraulic material is slag. So what happens to the calcium to silica ratio of a latent hydraulic material? Okay. Anyone else wants to comment on that? Okay. Yeah. So here the calcium to silica ratio generally in the latent hydraulic materials is close to 1. Yeah, slag is an example of latent hydraulic material. Yes. So let's move to the next one. Choose the material from below which has a similar composition as that of silica fume. I'm not telling exact composition. It's just that it is similar to silica fume. So silica fume has very high percentage of silica, right? More than 85, 90 percentage of silica. So which is the material which has a similar composition as that of silica fume? Yeah. So options are fly ash, metakaolin, GGBFS, and rice husk ash. So GGBFS, ground granulated blast furnace slag. Okay. So the correct answer is rice husk ash. Like all those who have commented it correct. That is option D. That is rice husk ash. So it contains silica in a higher amount. So where does that silica come from? Any idea? How does rice husk ash gets the silica? So silica fume is basically from the industry. So rice husk ash is it's a biomaterial, right? It's a biomass ash, you can call. How does silica get into that? Can someone put it in the chat box or can someone unmute and convey? Mm, due to controlled burning, we get reactive silica. I'm just asking whether it is controlled or uncontrolled burning, where is the silica coming from? Okay, actually, this silica is coming from the soil. So it takes nitrogen, phosphorus, and along with that, the silica is coming from the soil. And basically, the rice husk is very much rich in silica. And rice husk ash, the actually what happens is they burn it without any control. Uncontrolled burning happens in the open field, which results in the formation of non-reactive silica, which is not useful in the construction industry. But if we are controlling the burning, controlling as in if we control the temperature at which it burns, like in an incinerator, or and also if we control the duration of burning, say 30 minutes at 600 degrees Celsius or something like that, then the silica will be amorphous in nature. So that results in the reaction or reactive form of the rice husk ash. Okay, so anyway, the material which has a similar composition as that of silica fume is rice husk ash. Okay, moving on to the next one. Slag is almost completely amorphous because of the rapid quenching of the molten slag. True or false? So slag also we collected from the industry, and the statement states that it is completely or almost completely amorphous because of the rapid quenching of the molten slag. Okay, I'm waiting for more responses. So, from the industry, what we get is in a molten form. It's very hot. So, we need to cool it down. We can either slowly cool it or we can rapidly quench it. So, the statement says that this molten slag is rapidly quenched, that means rapidly cooled, which results in the amorphous form. True or false? Okay, so the statement is correct. Actually, from the industry, we get a very hot molten slag and we rapidly quench it or rapidly cool it so that the slag stays as almost completely amorphous. So, let's move to the next question. Reactivity of GGBFS or ground granulated blast furnace slag is less than the reactivity of fly ash. State true or false. Again. Reactivity of ground granulated blast furnace slag is less than the reactivity of fly ash. Okay. Can Naveed say why is it a false statement? Yeah. Yes, please, Naveen. Are you speaking? Because we can't hear you. You're not muted. You're unmute only, but we can't hear you. Okay, I think there's some issue with his audio. Yeah, due to more calcium. And again, one more thing. It's related to the previous question. This ground granulated blast furnace slag is quenched, rapidly quenched, which results in an amorphous form. If it is very slowly cooled, it will result in a proper crystalline form, which is not reactive. As much as it is amorphous, it's better for us. So ground granulated blast furnace slag has a more amorphous structure than the fly ash. Fly ash is not rapidly quenched or anything. So as a result of which, fly ash has a lesser amorphous nature than GGBFS. As a result, the reactivity of fly ash is also lesser than that of GGBFS. So the correct statement is false. Yeah. Thank you guys for responding. Okay. Now the next question is, addition of pozzolanic materials such as fly ash increase the susceptibility to carbonation. Whether the statement is true or false. So pozzolanic materials such as fly ash, when you add to the system, it can increase the chance of carbonation. It's a fairly very easy question, so I guess all of you must know the correct answer. Okay, let's wait for a few more seconds. Okay, I'm a little bit surprised because the correct answer is true. So, what happens is that when the pozzolanic materials or supplementary cementitious materials, when they are added to the cement or that system, it utilizes the lime or calcium hydroxide. It reacts with the calcium hydroxide. The reactive silica reacts with the calcium hydroxide and form additional CSH. So one thing is that porosity gets more refined, or porous structure becomes more, it will become less and less porous. That is there. But one more thing is that calcium hydroxide is more utilized, or the lime is being depleted. So what happens is, when the carbon dioxide comes and attacks the specimen or attacks the system, it initially goes for calcium silicate hydrate itself, CSH itself, because CH, there's no enough CH. So CH will be depleted very fast. Then it will goes to calcium silicate hydrate. So the susceptibility for carbonation is more in the SEM based systems because of the less lime in the system. CH content is lesser when compared to OPC systems in SEM based systems. So that is why the susceptibility to carbonation is more. Okay. So the correct answer is true. But having said that, since the porosity is less and lesser, and also the interconnectivity of the pores are lesser, there is less chance that the oxygen and moisture can get transported through the system into the reinforcement if it is a reinforced concrete system. So the chance of corrosion due to carbonation happening on the steel surface is lesser, because it needs moisture, it needs oxygen to reach there. For that, there should be proper interconnectivity of pores. So it's basically a trade-off there. Because of the depletion of calcium hydroxide, there is high chance of carbonation, but because of the less interconnectivity of the pores, there is less chance that oxygen and moisture can reach the steel surface. So it's always a trade-off, but there is always a chance of increased carbonation in the case of SEM based systems. So let's move to the next question. Bleeding and segregation increases with the addition of fly ash in cementitious systems. State true or false. So bleeding and segregation increases with the addition of fly ash in cementitious systems. Okay, Naveed says false. Rao says false. I'm waiting for more responses. If some are there, yes, Sri says false. Okay, so moving to the answer. The correct answer is false. Why? Because fly ash, it has a more specific surface area. It is finer than cement. So what happens is that the system has more fines now than the simple OPC system. Now the fly ash, which is a finer material, is added. The number of fines in the system has increased, which result in a lesser bleeding and lesser segregation. So with the addition of the fly ash, actually we experience a decreased bleeding and segregation. So the statement is a false statement. Okay, moving on to the next question. The average particle size of silica fume powder is dash that of cement. I knowingly, deliberately included powder because it is available in the dense form as densified silica or in a powder form or in a slurry. So what I'm asking for is the particle size of silica fume powder. So what is the average particle size of silica fume powder? Is it lesser than that of cement, or is it more than that of cement, or is it same as that of cement? Thank you, Naveed, for answering again. Anyone else? Rao sir also says A. Okay, so moving on to the answer. The correct answer is A, lesser than that of cement. So cement, basically the average particle size, it must be around 15 microns. But in the case of silica fume powder, it is even lesser than 1 micrometers. So it is less than 1 microns. So the average particle size is lesser than that of a cement. Okay, moving on to the next one. The technique which is used to determine the specific surface area of silica fume. So there are several techniques which we can use to find the specific surface area. Now we know that it is having a very small size, it's having higher fineness. So what technique will you use to determine the specific surface area of silica fume? Option A is mercury intrusion porosimetry, option B BET, option C Blaine's air permeability test, and option D X-ray diffraction. Naveed has answered. Okay, who else? Okay. So the correct answer is BET because generally we can use Blaine's air permeability and all to find the specific surface area. Clearly, mercury intrusion porosimetry is not the one. It is to find the porosity or pore size distribution. BET and Blaine's are used for finding the specific surface area. X-ray diffraction is to find the composition. So for composition investigation, we can use XRT. So Blaine's cannot be used because silica fume is very fine, as in the fineness is much higher and it has a very small particle size, having a size less than 1 micrometer. So in that cases, we cannot go for Blaine's air permeability because air has to permeate in between. So because of the difficulty, we cannot use Blaine's air permeability. We have to use BET using the adsorption technique. So we'll learn about BET in detail in the coming sessions. So moving on to the next question. Use of silica fume in cementitious mixes does not change the water demand. it decreases the water demand, and C, it increases the water demand. So this is also related to the previous or the question before that. Use of silica fume does not change the water demand, it decreases the water demand or increases the water demand. So what happens when silica fume is added into the cementitious mixes? Okay, let me wait for 1 or 2 seconds more. Okay, so when you add silica fume, because the specific surface area is much higher, it needs more water for workability. So otherwise, the mix will not be workable. So it generally increases the water demand. So this is one constraint in using silica fume, though it has higher amount of silica. We restrict this usage maybe to 5% like that. So why? Because adding more and more silica fume increases further the water demand. So that is one constraint with using the silica fume. Okay, moving on to the next question. Use of silica fume in cementitious mixes decreases ASR. So ASR is alkali silica reaction. So the statement is that alkali silica reaction or the susceptibility to alkali silica reaction is decreased in the cementitious mixes with silica fume. How does it affect? So how is it coming into action? Is it by deactivating the silica aggregates, or formation of a protective film around the aggregates, or capturing and binding the alkali in the system, or dissolving silica from the aggregates? You can think and then answer. So when we add silica fume into the cementitious mixes, it generally shows a lesser alkali silica reaction tendency. How does it happen? Is it because it just deactivates the aggregate silica aggregates, or it forms a protective film around the aggregates, or it captures and binds the alkali in the system, or it dissolves the silica from the aggregates? Okay, so let's move to the correct answer. The answer is C. So it doesn't at all act on the aggregates per se, it acts on the alkalis. So it binds the alkalis towards silica. So what happens is that that alkali is not available for the silica in the aggregates. Now why is it not reacting with the silica in the silica fume? That is because of certain size constraints, because silica fume the silica is much very fine. So because of such reasons, that silica fume will not cause ASR. Rather, it will capture the alkali in the system and binds it so that that alkali will not go into the aggregates and react with that silica. So the method of operation is it captures and it binds with the alkali in the system. It doesn't form any protective coating, or it doesn't deactivate alkali silica, or it doesn't dissolve the silica from the aggregates. Okay. Okay, moving on to the next one. The fire resistance of silica fume concrete. So that is one major problem for the silica fume concrete. It has lesser fire resistance compared to normal concrete. So how can we improve it? By addition of polymers, by addition of plastic fibers, the addition of viscosity modifiers, and by enhancing the dispersion of silica fume. Basically, silica, when you add silica fume into the concrete, or when you replace it with cement with silica fume, because of the very small size also, the matrix become more dense. So it doesn't have more open pores like in the case of normal concrete. So as a result, when there is a fire happening, the gases and the vapor, for it to evaporate, there is no place. So as a result, the concrete fails. If at all the vapor could move through the pores, connected pores outside, well and good. But in the case of a fire happening, if there is no place to go for the vapor, it is detrimental to the structure. So basically, that is a problem with silica fume concrete. It has a very less fire resistance. So how can you improve it? Addition of polymers, addition of plastic fibers, addition of viscosity modifiers, and by enhancing the dispersion of silica fume. Okay, thank you, Naveed, Shrish. Let's move to the answer. The correct answer is option B, addition of plastic fibers. What happens is during the time of a fire, because of the very high temperature, the plastic fibers melt and it forms a connected pore to the outward region. So it melts and forms a way for the vapor to escape. That is how it sacrifices itself and saves the concrete. So addition of plastic fibers is practiced to improve the fire resistance of the silica fume concrete. So the correct answer is B, addition of plastic fibers. Okay, moving on to the next one. Cement with slag replacement is used in marine environment due to its chloride binding, sulfate binding, CO2 binding, or sodium binding. So, in generally in the marine environment, cement with the slag replacement is used, and what makes it the better um, choice than OPC because of the chloride binding or sulfate binding or CO2 binding or sodium binding. Okay, moving on to the answer. Okay, it's not A or B, it's A. Slag has a tendency to capture the chloride and binds the chloride so that it will not go deeper into the reinforcements in the reinforced concrete structures and corrode the steel. So it has a tendency of chloride binding that makes it the better mix than OPC to be used in a marine environment. You're right for sulfate because sulfates are also seen in the marine environment, but generally the slag is used because of its chloride binding capability. Okay, moving on to the last question, I guess, for today. Yes. So, dash activation happened when slag is mixed with cement. Or, yeah, so let's move this part. Dash happens when slag is mixed with cement. Alkali activation happens, sulfate activation happens, or mixed activation. When slag is mixed with cement. All three. All three is C, no? Okay, so the correct answer is C. That is when a slag is mixed with the cement, it requires an activation, right? In order to react, if some activation is there, the better. So the type of activation, the alkali activation and the sulfate activation happens, that is mixed activation happens in the case of slag mixing with cement. Okay, yeah. So that's all for today. Let me, yeah, stop sharing. Okay. Yeah, I guess that's all there for mineral admixtures for week 6 section. So let's meet next week with the continuation of week 6, that is on week 7. It's also a continuation of mineral admixtures. Thank you guys for attending today. Let me